Our next speaker, and the final speaker for today, is joining us remotely. Vahagn Mikaelian. I'm sorry if I didn't pronounce that correctly. I'm trying. He's joining us from the American University of Armenia, and he's going to tell us about the effectiveness, constructiveness, or explicitness of the Higman Embedding Theorem. Take it away.
First of all, I would like to very much thank the organizers for such a great opportunity to talk at this scientific event, right? Now, this talk is going to be the famous Higman Embedding Theorem of Graham Higman, a great British mathematician. And now this talk is going to present our recent research on this topic. Namely, it is going to present this, let me outline it, this algorithm from our very recent preprint and from other recent research. As you see, I mentioned here all the archive links so that everybody can check the details. Now, which Higman theorem we are talking about? We are talking about, of course, the famous Higman Embedding Theorem of 1961, in which Graham Higman proved that a finitely generated group can be embedded into a finitely presented group if and only if it's recursive. Well, I wish to leave aside formal definitions in mathematical logic, but under recursive group, we understand a group in which the relations can be somehow described by an algorithm, a Turing machine. Of course, we are leaving aside the formal definition. Actually, this theorem is correct not only for finitely generated groups, but also all recursive groups in which not only the generating sets can be recorded by an algorithm, but also the generating sets, which can be not only finite but countable. It is effective. So we have whatever way to write those generators as x1, x2, ... So then the relations come R1, R2, etc. ... Now, this theorem is not explicit. We will talk about a little later. But the purpose of the algorithm which we are suggesting in this preprint is to give an explicit version of the same theorem and to solve some problems, including a long-standing problem, by means of this algorithm. Moreover, which is interesting, the finitely presented group which we are talking about can even be two generators. So two generators are enough to contain such a group. Now, let's give some historical characterizations of Higman's construction. First of all, I would like to mention that neither Higman or his descendants, students, etc., had ever stated that Higman's embedding is explicit. Moreover, I remember an article of Johnson, who is a student of Philip Hall, so he wrote an article in which he built explicit versions of Higman embedding for some special groups. And in this article, he especially mentioned the embedding of the additive group of rational numbers. And he stressed that is the main objective, his main objective, embedding of Q of this group Q is continuing to elude him. And he is stressing that this problem was set by Higman himself. So this I will display the source of Johnson's paper very soon and solutions of this problem. And one more problem, embedding of the group of n by n matrices over Q, which is of course again recursive. How to embed this into a finitely presented group. Unlike the problem of embedding of Q, which was solved recently, the problem of embedding of GL and Q still is unsolved. So I just mentioned that Higman and his descendants never told this embedding is explicit, but in the mathematical literature, interprofessional sources, there are interesting references about this, interesting mentioned about this, and I would like to mention, to bring here two of them. Namely, in 1973, Valiev, who, by the way, has an alternative proof of Higman's theorem, he mentions, so Higman's proof is constructive. We are going to stress what constructive means soon. So it is constructive in the sense that from constructive description of the group G, one can, in principle, extract a description for the finitely presented group, but this construction is so vast that this is practically impossible to do. So Valiev says it is constructive, but it is practically impossible to do this. And the second mention, which I want to stress, is a very recent interesting article of Britson and Nyberg-Broda, in which they mention that Higman's Higmanic theorem is effective. So see the different word, not constructive but effective, but it leaves open the challenge of finding natural embeddings for particular groups. So here are the sources in which those citations can be found. Very soon, we are going to state if or not Higman's theorem can be called constructive, effective, etc. So our road plan is the following. First, let us make clear which terminology we use, what we understand, recursive, explicit, constructive, etc. Then, after stating those terms, we are going to mention if Higman's construction is effective, constructive, recursive, etc. And then we are going to refer to again to our preprint, in which the algorithm, explicit algorithm, has been constructed, and in which it is in detail explained if Higman's embedding can be called effective, etc. So first things first, let's terminology. Of course, from book to book, mathematical terms may differ a little tad. So, but fortunately for us, there is widely accepted consensus in mathematical logic what is effective. In this case, in particular, I am referring to the book of Davis and Rogers, classical books in mathematical logic, and why these books are valuable not only because they are classical books, but also because Graham Higman himself, in his article, which we are discussing, is stressing that all his terms concerning mathematical logic are based on the textbook of Davis. So by relying on this book, we are confident that we are in the same boat as Higman was. So by these fundamental books, a procedure, a process is called effective if there theoretically exists an algorithm or a Turing machine which is executing that process, which is doing that job. I want to stress that we are talking about theoretical existence of the algorithm, not explicit construction of this algorithm. It is enough to state that such an algorithm somehow exists. And in this context, as many group theorists may be present, I wish to stress an example which is very clearly explaining this point. This example is coming from the book of Rogers, in which he brings the following example to describe effectiveness. The following is a fully correct example, fully correct algorithm, effective algorithm. Here's that example we start. Well, the number pi, which is equal to 3, 1, 4, 1, 5, 9, whatever. Does this number pi somewhere in its decimal form have 10 digit 7 standing in the row? Currently, as Rogers mentioned, this is an unsolved problem. Nobody knows if such a tuple of 777s or 10 times occurs in pi or not. But we can be confident that this question has exactly one answer, either yes or no. No other alternatives may be present. So I can write an algorithm to effectively define a function f on just the number 0. F0 is equal to 0 if such tuple of digit 7 does not exist, and F0 is equal to 1 if answer is yes. So nobody knows if such a tuple does exist or not, but this algorithm is absolutely correctly defined, and it is effective without giving an answer how to actually apply this. Maybe 5 days later, somebody discovers the answer to this question or not, but this doesn't bother us. So this was an example what effective is understood in the modern world. A procedure is recursive, the other word, if it, by according Kleini characterization, again, it can be found in all math logic books, if it can be obtained from zero, successor, and the projection functions by means of composition, primitive recursion, and minimalization. Although this sounds very differently, effective and recursive actually are equivalent notions. They are practically the same. This fact cannot be proven. Actually, it is true according Church Turing thesis. Another word, again widely used, is computable. So computable, recursive, effective. In most books are simply synonyms. The same set can be called recursively enumerable or computably enumerable, etc., etc. One more word about these topics is constructive. I can refer to this another fundamental book. But unlike the previous three notions, constructive means there should explicitly exist a construction which does that procedure. So the previously mentioned example with the number pi is not explicit, it is not constructive. And we are using the word explicit in the same sense as constructive. So after stating the terms, let us come closer to Higman's construction. Section 3.2 in the preprint we are mentioning is called Is Higman's Embedding Explicit? In this section, we are in detail discussing Higman's steps and identifying steps of this sort, which actually suggest no actual algorithms to perform them. They are just relying on some recursively enumerable constructions. If we have time at the end of this talk, we will talk more about them. And also they are hurdles of type 2, steps which actually can be called explicit, but which are requiring such an astronomical numbers of steps that it is practically impossible to do. Of course, the fatal obstacles here are those of type 1, which suggest no algorithms, at least inside Higman's articles itself. So based on this, we say that, let me just bring an example, very simple example. Just to point a fragment of Higman proof, which suggests no algorithm. Suppose a group is given by its generators and defining relations, right? Higman is writing or translating the defining relations to some tuples of integers. How does he do this? He considers a two-generator group. And look at these two free groups. One free group is that coming from the this description of G by generators and defining relations, and the other is two-generator group. As your group is recursive, this f sub x must be at most countable. Any at most countable group, free group, is embeddable into a two-generator free group. There are many textbook methods to do this. And after this embedding, this allows to write every defining relation from this set R to rewrite in just two letters XY. After we did do this, the newly written, the updated relations look like something like this. So they consist of tuples, which are the products of powers of x and y. Now we are just taking those exponents, such as 3, 2, 1, -5, and writing them as a tuple. So this is a trip this is the path from a defining relation of G to such a tuple. Namely, first write group, embed this free group of countable rank into a two-generator group, then write each relation in this format, then from here output this tuple. There is no doubt, it is evident that if R is recursively enumerable, then the set of such tuples obtained, actually, it also is recursively enumerable. But Higman's construction provides such a huge set, and in the next step of Higman construction, he just says take a recursive set of such tuples and write them, obtain them from two special basic sets Z and S by means of Higman operations, which are very useful tools defined in his article. So this step, which I just mentioned, is evidently recursively enumerable. But how to do this process? This is not given at all. So this is one of the fragments, I wanted to stress it, which is telling us Higman's construction cannot be called explicit, cannot be called constructive, and we regretfully cannot, we are not able to agree with Valiev's reference. But all those steps that we mentioned above still are keeping Higman's construction effective. So the statement of Britson and Nyberg-Broda is absolutely correct. The Higman's construction is effective, although it is practically impossible to apply to whatever, even simplest example, even for the group Q about which we talked a moment ago. Valiev's statement is, we cannot agree with it because the problem is not in many steps or vast amount of steps. It simply doesn't contain an algorithm for some of its steps. Now, which modifications we apply to those steps to make the whole story effective, explicit? In chapter 4 of this preprint, we are outlining the basic changes which we are going to do, and then in chapters 5 and 6, we describe how all those changes are being done, and we fully argument our algorithm. Then I'm glad that we still have a few minutes, so I can talk about an application of that method. In recent 2 articles, especially this one, which appeared a few months ago in Journal of Group Theory, we are taking the group of rational numbers. This is its representation by generators, which are countable, and by its relations, which evidently are recursive. And we embed this group into a finitely presented group. I would like to outline a few sources. One of them is Johnson's article. I just mentioned it a few moments ago. Then the same problem, if or not Q is embeddable into a finitely presented group, is mentioned in Gorovka notebook, here, the source, and it is also mentioned in the book of Pierre Delard, Topics in Geometric Group Theory. I really enjoyed this book. Okay, so these are the sources in which this problem has been explicitly mentioned, and this year's article is containing an explicit overgroup containing Q, and moreover, which is interesting, we also are building a 2-generator group just with 2 generators, which is explicitly given. Of course, it has many defining relations, 2 pages long, but it does contain the group Q. Earlier in 2018, we were able to present this embedding method, yet without any proof, in the conference dedicated to the memory of Alexander Gurosh. But another very interesting embedding of Q into a finitely presented group has been obtained in 2022 by Bell, Heidi, and Metucci. Their construction is very interesting. It is not based on Higman methods. Higman's method basically are all relying on free constructions of different types, free products with amalgamation, Higman-Neumann products, etc. Their construction is using the piecewise linear homeomorphism on R, the automorphism group of Thompson's group, some special very interesting groups, etc. Now, I had actually built one more section. As you see, I wasn't sure if we are going to have time, and I call it optional. But so this section shows which obstacles we would get if we try to directly apply the Higman embedding theorem to Q. As you see, then we are going to get such very vast sets of generators, giving birth to even bigger set of such tuples sequences, which don't let us build the job properly. Anyway, we don't have time to talk about all those details, and it remains me to remind you that the preprint with algorithm which we're talking about is available in archive, and it is a pleasure to thank you for the opportunity to deliver this talk to this scientific event. Thank you very much.
Do you have any questions? No, but you can hear the room properly, so I'll stand here. So I have one question about the effectiveness of this algorithm. Is it fast in the sense that you could quite quickly construct? Sorry, I need to formulate it properly. So I'm wondering if by constructing embeddings quickly, there might be an application to sort of largeness properties of groups by embedding known big groups inside other ones.
Okay, since this system is interrupting your word, may I please restate your question to make sure you and I understood everything correctly?
Sure.
So your if I understood correctly, your question is: after this algorithm is built, all the steps are done, is it relatively easy to do the job after all preparations?
Yes. Yeah.
Great. So I very much regret to say that even after all such preparations, unfortunately, this algorithm which I was mentioning is far from being simple, far from being elegant and beautiful. I am not sure Higman himself would like that algorithm, because his constructions usually are short, beautiful, and all of them contain brilliant ideas. So my construction consists of many steps, but unlike the original methods, which require really huge steps, my steps are more or less possible to do. So I was able to write on a couple of pages the exact representation by generators and defining relations, finitely many, a group which does contain Q. Although the process cannot be called very simple, elegant, beautiful.
Okay. Were there any other questions in the room? If not, let's thank Vahagn again. Let's thank all of our speakers for the first day.